All right, so in this video, we'll look at the last goal, the third goal of the limits unit, which is to be able to find limits at infinity. If you watch the other two limits videos, hopefully you realize what limits are doing is we're approaching an x value and seeing if the y values approach something. So in the other videos, we were looking at approaching an actual x value. So we might choose any number on the x-axis and sort of march closer and closer to it and see if the y's got closer and closer to something. In this, a limit at infinity will basically talk about, instead of going towards some number, it'll talk about what happens as we make the x's go toward either positive or negative infinity, meaning making them very, very, very large or going in the negative direction large. All right, so we want to see then, as we make x super large, do the y values approach something or do they not approach something? So that's basically what this is about. Because infinity is not actually a number, we can kind of talk about what happens as we go out toward infinity. If we go to the right of the graph forever, the left of the graph forever, what do the y values do? Do they approach anything or not? All right, so the way this gets symbolized, a limit at infinity, is basically uses this symbol. We say as the limit as x approaches infinity, what this means is as x gets bigger and bigger and bigger on this function, if there is some y value that it approaches, that's the value we put here. So just like other limits, if the limit exists, if the y values do approach a number, we'll report that as our answer. If the y values don't approach anything, if they're maybe getting infinitely large themselves or they're bouncing around and they're not really getting closer to any number, then we can report that the limit doesn't exist and we can use DNE as the abbreviation for that. All right, so these may or may not exist if, as x goes to infinity, the y values of the function do something, we put that out here. That's what this says. What this means is as x gets larger and larger, f of x, which is the y values, they get closer to some real number L, all right, if that's the case. So if you say this expression, that's what you mean. You can also go to negative infinity. It's weird. You have to be careful about saying larger or whatever, because remember, things to the left on the number line are actually less than things that are on the right. So technically, negative infinity is the least quantity. It's the, something that's all the way to the left is less than all the other things. But I would think about this as just big negative numbers, right? So like negative a million, negative a billion, those are way, way, way to the left. They're technically less than, numbers that are to the right of them. But you can think of them as being negatively large, all right? So even though technically they're less than. So basically this means as you go to the left, more and more and more to the left on the number line, does the function y values approach something or not? Once again, it may approach something, it may approach the same number as the positive one or a different number, but also it may not approach anything. It may, the y values may go up forever or down forever, or they may bounce around or crazy stuff, all right? So we're going to use a table just like the other ones to sort of get an intuition of what's going on, all right? So here's what you do for limits to infinity. So probably should have covered this up. I guess it's too late now. So let's look at the problem and then the table I used to solve it. So the example at the top says it wants us to find the limit as x goes to infinity of 3 over x squared. So the thing that's different about the table is, since we're not approaching a number, but we're approaching what's considered like an infinitely large quantity, or trying to get larger and larger and larger. Now, infinity is not actually a number. There's no point where you actually get to infinity. Any number you pick, you can just always make it bigger. So the way that we figure out what's happening with infinity, since we can't actually get there, we can approach infinity in theory by making our number larger and larger and larger. So when you go to make the table, these tables will, for infinity, will always be one-sided, because you can't get to infinity from both sides. The only way to sort of approach infinity is to keep jacking up your x values larger and larger. Now, you can technically pick any number so long as they get progressively larger, but to make it easy, I basically picked like a kind of big number, a bigger number, an even bigger number. By putting more zeros on it, you're making the number ever larger. You don't have to pick these particular numbers, but the idea is to pick a kind of large number and then keep jacking up the number larger and larger to see what the y values are doing and see if you can catch on to a pattern. Now, for these, I did 4 values. Usually, if you do 3, 4 values, you start to see what happens. If not, you could do more. Usually, you'll kind of see a pattern, at least on the examples that I'm going over and giving you. There's nothing too crazy. You should be able to tell what's going on. So I want to give an answer to this. And what would the answer be? Well, you set up a table like this, and basically you want x to go to infinity, so I'm just making x larger and larger. And the answer to this is whatever the y values of this do as the x's get larger. So if I look at the y values, well, when I plug in 10 into this, and you could do that, once again, in the calculator. I should probably show that, but if you watch the other 2 videos, basically you shouldn't be doing this if you haven't seen the other ones. But if you saw the other videos, remember you can go into the y equals, put in the function, and then if you go into the table set, so you hit second and window, that's that button, you can go in, you can set the independent to ask. The independent variable is the x variable, and then you can go to your table and you can basically enter all of these values. So I'll show you them. Let me just give a second to enter them here. So now one thing to note in the calculator is how the calculator displays it. Try and get so it's not so blurry. So notice it said 0.03, and that says 3e to the negative 4, 3e to the negative 6, and 3e to the negative 8. Remember, this e is standing for scientific notation. The negative is telling you to basically take 3 and move the decimal point over however many slots that it says. So negative 4 means to move it 4 to the left. So when I'm putting these in the calculator, this one said 0.03. Now, for the 3e to the negative 4th, I would take the number 3 and just move the decimal point 1, 2, 3, 4 slots to the left. So I'm basically getting 3 zeros and a 3. The next one was 3e to the negative 6. So I would take 3 and move it over 1, 2, 3, 4, 5, 6 decimal points. So it gives me 5 zeros. And then the next one would be 3e to the negative 8. So I'm going to move it over 8 spaces and basically get 7 zeros. All right, so make sure you know how to interpret those, because the calculator doesn't just give you the decimal, it puts it in that, most calculators will give it in that weird notation. So just make sure you understand what that means. Basically, this is telling me the numbers are getting progressively tinier. So what does this mean? Well, these numbers here are actually approaching 0. When you get tinier and tinier and tinier and tinier, you're basically shrinking the number down to nothing. Now, these aren't ever 0, but they're getting ever closer to it, right? You're getting less and less and less of whatever you had. So my answer to this would be, well, as x approaches infinity, as the x's get larger and larger and larger, what are the y values doing? Well, the y values are getting tinier and tinier and tinier. They're approaching 0. So basically, if I wanted to answer this, because remember, the limit's supposed to tell you what's the y value you're approaching if you're actually approaching one. It'd be nice if this thing actually, I want to put the answer down, but hello. There we go. Took long enough. So the answer to this would be that this equals 0. Man, doesn't want to cooperate. There we go. All right. So what is this value? Well, the limit is 0, because basically it looks like these y values are going to 0. So as this function goes to infinity, we actually do get a value for y. The y's go towards 0. Look at a couple others. Here's just another one. This one has the limit as we go to infinity for this big chunky function. Now, once again, I wouldn't do this by hand. Just throw this function into the calculator, and I can use the same values. If I want to go to infinity, well, I tried 10, 100, 1,000, 10,000. Once again, I could keep going. But once I got to 10,000, I could see what was going on. So if I put these into the calculator, what happens is when I plug 10 into this, it comes out to be 1.686 roughly. When I plugged 100 into it, because 100 is even bigger, well, as I plug 100 into this, so I plug in here, 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 and here, and see what the calculator gives me. And like I said, the table will do that for you. It gave me 1.969. And once again, that's rounded a bit. It keeps going. Once I plug in 1,000, 1,000's even bigger than 100. Well, it gets even larger. It becomes 1.997. I plug in 10,000. Once again, that is rounded as well. Plug in 10,000, and then I get 1.999. I think it was 9997. But now I'm hoping the pattern's clear from here. I mean, I could do a bigger number and see what happens. But this was at 1.6, then it was 1.9, then it was 1.99, now it's 1.999. So as x's go to infinity, what's happening to the y values? Well, the y values look like they're approaching 2, right? 1.99999, whatever, is getting closer and closer and closer to 2. So the answer to this, once again, I'll try to put it up here. Hopefully it cooperates with me this time. There we go. That was a lot faster than last time. What is the answer to this? Oh, Q. 2. So because as the x's get larger, the y values look like they're going toward 2, I'm going to say that the answer looks like it's 2. Let's look at 2 more. Here's an exponential one. Now, if you remember from algebra, exponential functions can grow really large. But this time I decided instead of to look at the large side, I looked at the negative side. So if we actually did this for positive numbers, 2 to the x would get larger, 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 larger. It wouldn't have a limit. But I want to show you one with negative infinity. So this says the limit as x approaches negative infinity. It means instead of going to the right, we want to keep going to the left with bigger negative numbers, right? We want to go left on the number line. So what happens to 2 to the x when we go to the left all the way? Well, you could figure this out by, instead of plugging in 10, 100, 1,000, well, we want to go to the left, so plug in negative 10, negative 100, negative 1,000, keep going to the left. Now, technically, I probably should have shown it going that way, right? I probably should have done negative 10, negative 100, negative 1,000, but I figured I'd keep the pattern from before that I'm making the numbers, in theory, get progressively larger. Technically, they're negative, so they're getting progressively less. But I'm jacking up the size negatively. So starting at negative 10 and then going to negative 100, negative 1,000, negative 10,000 is going to give me an idea of what's going on. So this is what I got in the calculator. And I want to talk about these values because technically the calculator's only as good as its programming. The calculator's technically wrong, but it gives me the answer still. So where is it wrong? Well, when I plugged in negative 10 into this, so 2 to the negative 10 is going to give a tiny number, 0.0009. When you go to negative 100, so you start getting closer to negative infinity by going to the left more. When you plug in negative 100, you get 2 to the negative 100. That's a really tiny number. Basically, it's an 8, and you have to move the decimal point 31 places to the left. That means you have a decimal point, 30 zeros, and an 8. That's an unbelievably tiny, tiny, tiny number, right? So it looks like this is going towards 0, right? This is tinier, this is even tinier, and like that other example I did, when that happens, it's going towards 0. Now, here's where the calculator is technically wrong, because when you plug in negative 1,000 to this, it's technically not 0, but the calculator, it becomes so tiny, the calculator can't even tell the difference between the number it gets and 0, right? Because think about, if it's the calculator go up to 8e to the negative 99, after that, it can't calculate any smaller. It doesn't have enough memory or space to do that. So if you go beyond negative 99, the calculator, it's so tiny, it just displays 0. So the calculator essentially says this is 0. It's technically not 0. It's a number so unbelievably tiny that the calculator can't tell the difference between it and 0. But just realize technically the calculator's wrong. It's rounding it off here. It's basically super tiny. It's just saying 0. And this is even tinier than the number before, but once again, it's so tiny it can't display it, so it just goes with 0. So realize that the calculator's technically, it's an error because it's rounding it to 0, but you can't blame it. It's so tiny it can't display it. But basically, the good news for you is that even though these technically aren't zero, it supports the fact that the limit seems to be going towards zero, right? We get a tiny number, a unbelievably tiny number, and then numbers so tiny that the calculator can't tell the difference. So basically, the answer for this one is zero, unless the calculator kind of gives it to you when it can't display the proper answer. So once again, the limit for this one is zero. So that's our answer. All right. And then just to show you one that doesn't exist, so you've seen one, and also a caution for being careful why I do several values. This is the limit as x approaches infinity of sine x. Now, I haven't really talked much about these graphically. If you take a calculus course, or you guys who take AP Calc, we will, and you'll learn a lot more about these. But one thing to think about the limit as you go to infinity is, remember, if you're going to the right forever, does it approach anything? If you remember what the sine function looks like, it's a wave. It goes back and forth, back and forth, back and forth. So if you know that, as you go to the right, the sine curve doesn't really approach anything. It just keeps bouncing back and forth. But how do we answer this with a table? This is why you do several values, because you got to be really careful. I'm still going to jack up the values 10, 100,000, 10,000. And one thing to be careful with when you do trig functions is, unless it says otherwise, you want to be working in radians, right? So these values I got from putting the calculator in radian mode. All higher math is done radians. So unless it says otherwise, I want this as radians go toward infinity, not degrees. Even though the answer is the same for degrees, you won't get the same y values. So make sure that if you're doing any trig stuff, you have your calculator in radian mode. Now, the thing I wanted to point out with this is it technically doesn't have an answer, but this is why you have to be careful, because some people go, oh, why don't I just put in one number and see what happens? I'll put in just a really big number and see what's going on. You have to be careful, because as you progress, you want to see what the pattern is. Putting in one number isn't always going to give you the answer, like in this case. Say you plug in just 10. Well, it's about negative 0.544. You may get tricked and think, okay, well, negative 0.544 is close to negative 0.5. It's close to negative a half. In fact, if you're not careful, you go on to 100, and kind of coincidentally, it gets closer to negative a half. It goes negative 0.506. So if you just stopped it there and were like, oh, well, I see negative 0.54, negative 0.50, and you don't explore it a little more, you start to think, oh, maybe it's going toward negative 0.5. This is why we do a few values to make sure the pattern continues, because then you go to 1,000, and when you plug 1,000 into this, you get 0.8268. And suddenly, this isn't going toward negative 0.5 anymore. Now it's at 0.8, so what happened? The next one is negative 0.3056. So now it's kind of strange. It's like bounced back to negative 0.3. And actually, if you go to the next one, I think 100,000, it's a decimal, but it's positive again. And what you'll find is if you continue this pattern out, these numbers don't approach anything. They're just kind of randomly bouncing back and forth. And like I say, if you understand what the sine function looks like, the sine function sort of bouncing back and forth. You sort of just randomly pick in certain spots, and sine always goes back and forth on the y-axis between 1 and negative 1. So these things are really just kind of randomly bouncing between 1 and negative 1. But I figure I would show this because, number one, it's one that doesn't exist. So here's a limit as we go to infinity, and we don't really approach anything. So we'll say d and e. But it's also important to see that sometimes you may get tricked. There may be a pattern that starts, but that's why we do a few values to make sure that that pattern continues. So then to finally give the last answer to this is an example of one that does not exist. So we can just say either does not exist, or like I said, the classic thing is to put d and e, right? So what is the limit as x approaches infinity of sine x? It doesn't have one. It's the y values aren't approaching anything. All right, and another way that things could also not exist, because sine bounces back and forth. Remember, if anything starts becoming infinity or negative infinity, so I'll just go back briefly, talk about this. This went toward negative infinity. If you actually did this for positive infinity, if you did positive 10, positive 100, positive 1,000, so on, you'd find these numbers getting super large. If you were going toward the positive side, 2 to the 10 is a huge number. Well, I guess it's not unbelievably huge. It's 1,024, but it's pretty large. 2 to the 100 is really, really large. And then 2 to the 1,000, it starts to get to the point where I think the calculator can't display it anymore. So if we were on the positive side, these numbers would be getting bigger and bigger and bigger, and they would be approaching anything, and we'd just say DNE. And if you know what this graph looks like, 2 to the x is exponential, so it goes up on the right side and flattens on the left. That's what the limit's kind of telling you. If you go to the right, the thing goes up forever. If you go to the left, it flattens out and wants to go toward 0. All right, so that's a bit of a connection with some of the graphs that we've done, because we've looked at graphs of exponentials and graphs of trig. And like I said, if you go on and take calculus, we'll connect these with their pictures. It's just difficult to do all this with this online teaching stuff. But all right, so that's limits at infinity. That's actually the last limits lesson that I'm going to do with you. All right, so I will put up the assignment once again. If you don't have a graphing calculator, use that website. I will link it once again to the assignment. But if you want the explanation of how to use it, you got to go to the first lesson. All right, but you can use that website the same way I use the calculator. Go to the table and just plug in these really big numbers. Make sure you enter the function correctly, and it'll give you these values. And any function that you can put in. Remember, with the online one, you have to use like a caret. I haven't actually done trig functions on it, but I didn't give a trig function on the worksheet, so you don't have to worry about it. But just keep in mind for the future, trig functions need to be in radians, and I would hope that website calculates radians, but like I said, I'm not actually making you do it. All right, so this is just to show you one that doesn't exist. You'll basically have, some that look like these that you can enter. All right, so that ends this lesson and ends the unit. All right, so take care and stay safe.